Everyone. My name is Anshita, and today I'm presenting before you. I will be talking about complexity, P, NP, NP hard, NP complete, and we'll also try to prove that a problem is NP complete. So let's start with the complexity. So first of all, there is P, which is basically polynomial time. These are the problems that can be solved quickly by a computer. That means the time taken is reasonable, even if the input is very large. The time grows like n square, n cube. So we call it polynomial. And these are the easy or we can say efficient problems. For example, let's say sorting a list of names or finding a shortest path in a map. So these are kind of P, polynomial time problems. Now, there are a lot of problems that we have seen previously. So let's just see few of like just go through those problems once. Like in polynomial time, we have seen linear search. There are binary search, then insertion sort, all of these problems like merge sort, matrix multiplication. These are all polynomial time algorithms. For linear search, it takes n time. For binary search, log n. Insertion sort takes n square. And then there is merge sort, which takes n log n. And matrix multiplication takes n cube. So these are all polynomial time algorithms. Then there is exponential time. In these, we have seen 0, 1 knapsack problem, which is like 2 power n. There is traveling salesman problem, and there are many more like sum of subsets. So these are, I think all of them are like 2 to the power n. So these are like exponential algorithms. Now, today we will be seeing P, NP, NP hard, and NP complete. So we have already seen what is like polynomial, right? Let's move on to NP. NP is basically non-deterministic algorithm. So it's like, let's say for an example, you have been given some array like 10, 8, 6, 9, 4, 2. And let's say the indices start from the number 1. And you have been given a key, which is, let's say, 9. So you need to find an algorithm which gives directly the indices of this key 9, which is 4, right? So how are we going to come up with that algorithm is the question. So just as an example, we can take a kind of pseudocode. So let's say you have some n search of, like, let's say an array of size n and the key is given. So here we are writing non-deterministic algorithm, okay? So n, like j is equals to choice, let's say. And if key, so we kind of give a condition like this. Let me just just for your reference, I'm writing this kind of and yeah, equal. So if you see this, this is kind of a research, okay? So right now you don't know what to fill in here, but in future, when someone comes up with the solution, with an idea, with a procedure, this will be filled. So right now we don't know what this choice is going to be, but we need to make sure that it's a constant time operation. So the algorithm will result in constant time, right? So this is how we kind of approach like not like this is like a non-deterministic algorithm uh, way of writing this. And this was just for an idea, okay? Now moving ahead, we can take it in like much more simpler explanation, if I would say, for a non-deterministic algorithm. You can say like output cannot be predicted. Like it cannot be predicted properly, even if we know the input. Like same input might give you like different outputs for different rounds. Let's say we have some initial state Q naught and we gave it an input 0. We got output Q1, right? We again gave the same input, and for the same input, we are getting some different output. So here what happened is same input, 0, but we get different outputs, right? For Q1, like different outputs, Q1 and Q2. So this is termed as non-deterministic. Now let's move ahead to a deterministic algorithm. So in deterministic algorithm, very clearly it's opposite of this, I would say. So so if you have like, let's say initial like some state Q naught and you fed an input 1, you're getting output Q1. Okay. Now you are feeding it an input 2 and you get output Q2. This is what deterministic algorithm is. Basically, you have different input and you get different output. So, coming back to non-deterministic uh, algorithm, this algorithm will take more than one path. Like we cannot determine the next step in this algorithm. Like only approximate solutions can be given, like no accurate solutions, okay? For an example, we have these problems, Monte Carlo Monte Carlo problem, or there is one more very famous problem, which is known as genetic algorithm. And there are many, many more of these. So these are non-deterministic. Now, we will be seeing one concept which we are highly going to use in this particular topic of proving a problem NP complete. This is known as reduction. So, what is it? Like, consider we have two decision problems, P1 and P2. And when I'm saying decision problem, what does this mean? Decision problem is any problem which gives you either like output, either yes or no. There is no numerical output, okay? So yeah, and if you have like some numerical output, just for reference, like it's called optimization problem. But this one is a decision problem, okay? So we are taking two decision problems, let's say P1 and P2, and you have this problem like P1, which has some input. Now, let's say input I1, and it has some algorithm, let's say A1, which is unknown to us right now. Like, we don't know what the algorithm is. And then there is a problem P2, which has some input, let's say I2, and it has an algorithm A2, which is known to us. Like, we know the algorithm in this case. So in reduction, what we say is if P1 is solvable using algorithm P2. One second. So basically, what reduction says is if P1 is solvable using P2, then P1 is reducible to P2. So, like, how are we going to solve it? Like, we just convert the input of P1, like, we convert input of P1, that is I1, to input of P2, that is I2. Like, in order to convert these, you need some functions, right? So let's just understand in this way that you have this input I1, right? This is your input of problem one, right? Then what you do is you apply some functions to it. And you need to get this, like you need to convert kind of input one to input two. And then you feed that input, sorry, you feed that input to this algorithm that we knew, which was A2, right? This algorithm was the known algorithm. Here you feed that input, and then you get the output, which is gonna be your solution to problem one. So this is what reduction is about. Like, you just kind of apply a function, convert the inputs, and then you apply it to the known algorithm. So that's how you get the output for the unknown, the problem with the unknown algorithm. Now, moving ahead to NP hard. So basically, a problem is called NP hard if like every problem in NP uh can be like polynomially reduced. So let's say you have some NP problems, let's say A, B, C, D, some problems that are like, these are all NP problems, okay? If all of these can be reduced to some X, like You have A, B, C, D, right? If all of these can be reduced to some x, right? Then it is called NP hard. That's the idea. So let's move on to the last one, which is your NP complete. Now, a problem is called NP complete if it is NP, first of all, and second of all, it's NP hard. So it needs to be NP as well as NP hard. Then we call it NP complete. So also, if you see P that we saw in the previous P that we saw previously, uh, no, sorry, yeah. So NP and NP hard. So any problem that we are seeing, right? If it's NP as well as NP hard, then we say that it is NP complete. So here, let's say you have some problem which is NP, and let's say you have some problems that are NP hard. Then this section, which is NP as well as NP hard, is gonna be your NP complete. Okay. So basically, it has to be non-deterministic algorithm and should also satisfy the property of NP-hard. That is, it should be reducible to X. So that's how we see whether a problem is NP complete or not. There are a lot of NP complete problems like SAT, 3CNF SAT, clique, vertex cover, ham cycle, TSP, subset sum, and a lot of more. So today we are going to see a problem which is X3C. Okay, so we're going to see why X3C is NP complete. So I'm going to make it a very simple explanation so you can understand it better. So uh, let's start with what the problem is all about. Like, just imagine you have 9 items. Okay, let's say we have some 9 items. It can be anything, like let's say colored balls. Okay, and it is numbered from 1 to 9. Now you're given bunch of small boxes, and each ball holds exactly. No, you're given bunch of boxes, and each box holds exactly 3 balls. Okay, so you have been given like bunch of boxes, and each box can hold only 3 balls. The question is, can you choose just 3 of those boxes? Like you are given an option to choose only 3 boxes, such that all the 9 balls are covered. There are no repeats and there are no leftovers. That's what we call exact cover by 3 sets or X3C. So let's just go and check the first property, which is whether it is an NP problem or not. So now, if someone gives us a solution like 3 boxes, like okay, someone gives us 3 boxes, we can easily check like, are there exactly 3 sets? Do they cover the elements? no duplicates, no leftovers, right? So this is very quick. We can check that in seconds. So we can say that X3C is NP because if we are given the boxes, we can easily check are there exactly three sets or do they cover all the nine elements? And also we can check if there are any duplicates or if there is any leftovers. And this will not take much time. It will take like seconds, right? So that's why this problem is definitely a NP problem. Now, the second property, which was whether it is NP hard or not. Now, let's check if it's NP hard. To prove it's NP hard, to prove it's NP hard, 1 second. Okay. So now let's just start with proving it, whether it is NP hard or not. Okay. So to prove it, it's NP complete. We need to prove both if it's NP and NP hard, right? And we use that by using the trick that we had discussed earlier, which is reduction. So it in reduction, we basically take a problem we already know is hard and then turn it into given problem. In this case, it's X3C. So we will take some hard problem and then we will um no, and we'll just turn it into this given problem, which is your X3C, right? So there is a famous hard problem which is called three-dimensional matching, basically 3DM. It's just like making teams of three players where each player comes from a different group, and we want to make teams where no player is reused. Like um, it's just like, how do I tell you? Like we have three players, and each of these three players come from a different groups. Let's say A, B, C, okay? And we want to make teams where no players are being reused. So this problem is already known to be NP hard. Sorry, NP complete. This problem is already known to be NP complete. And we will see reduction now. So, a basic idea, a reduction, as I talked before, is a way to say, like, if I can solve, say, problem B, then I can also solve problem A by converting A into B easily. So, solving B would be to like solve A, right? We saw that in the previously we saw we're just changing the inputs, like converting the inputs and trying to find the output using the known algorithm. So, like, if you want a better explanation, it can be like, imagine like baking a cake. If it's like, it's really hard. But if you can turn that cake recipe into a cupcake recipe in just a few more easy steps, and you find cupcake is easy to bake. So you're like baking the cake was tough, right? And in just few more easy steps, you find out that uh making cupcakes was like easy. in this case, there are gonna be two conditions. Like either the cake must also be easy to bake, or cupcake must be just as hard as the cake, right? So that is how we kind of prove something is hard. Now moving on to 3D matching, which is a known NP-complete problem. So here, what we're gonna do is we're gonna do polynomial time reduction in order to convert it to X3C, which is a new problem. Like this is a known NP-complete problem, and this is your given or a new problem. Now, proven to be NP-complete, right? Because we have already shown like this is NP, and we also saw that uh, this problem can be reduced. Now let's just take like an example, okay? Um, so let's see. Okay, so let's say you're given an universe, like you of three Q elements, and a collection C of subsets of size 3. Now, your goal is to select Q subsets that together cover you exactly once with no overlaps and no missing elements. So, how are we going to do this? Let's say we have sets X, Y, Z, and they have like Q elements. So, the total number of elements is going to be 3Q, right? So that becomes U is equals to X union Y union Z. This will be the universe for the X3C problem. Now, let's just create three element subsets like the collection C. Like for every triple, let's say X, I, Y, J, Z, K in some T. Basically, T is the set of possible matchings. Create a subset. So subset is gonna be this only. And add all such sets to your collection, which is C. That's it. These sets become the candidate of three sets, like for your X3C problem. This is exactly what we've discussed earlier. Like you take a function, you convert your input of first problem to the input of the second problem. The second problem is the problem for which the algorithm is known. And then just keep the Q constant. So the target in both the problem is to pick exactly Q sets, or you can say triples. So the solution to the 3DM instance is like a matching of Q triples with no repeated elements. And the solution to X3C instance is a selection of Q subsets that covers all the 3Q elements exactly once. And therefore, it's the same. Now, you would think why this approach is going to work. Because if you could solve X3C, you'd find Q, like three element sets that cover all the elements with no overlaps. And that directly gives you a valid 3D matching in the original problem. So if X3C were easy, 3DM would also be easy. which we know it's not. Therefore, X3C is NP hard. And here we go. Um, so this was it. This is it. Thank you for staying here and listening to my presentation. I hope you did learn something from here. Thank you so much.